Okay, well, picking up where the videos from last year left off, I find that the section I had numbered last year as 5.2 is actually 5.3, so we're further along than we thought. Yay. And where we're picking up is a review of Newton's second law. Newton had three major laws of physics and a whole bunch of other very useful stuff. And the first one we just went over, and this is the second one. The second law is often written as just force equals mass times acceleration. That's probably the most common equation you'll see stating Newton's second law. But it's a bit deeper than that, really. If you think about what acceleration is, it's a change in motion, either speed or direction. And because acceleration is a vector quantity, direction matters. So remember, if you're going around a circular track at a constant speed, you're still accelerating because you're constantly changing directions. Direction matters as far as acceleration is concerned. And of course, also force is a vector quantity. So direction matters for that also. It's only mass in this equation. It's a scalar quantity. Mass has no direction. And so Newton's second law is really about basically a cause and effect relationship between force and changes in motion, which is another way of saying acceleration. So here we have force versus acceleration. A change in motion, which would be like a change in speed or direction, is acceleration, as I said a moment ago. The net external force causes a change in motion, that is acceleration, and that's Newton's first law. And it's important that we use net force here because some force that's exerted on an object might be used up by things like friction, which is a force in the opposite direction that opposes movement. And obviously, if there's no movement, there's no acceleration. And if there's no movement, then there's no net force. Okay, so the forces that we're interested in are external forces to the object that we're concerned with. And that's because internal forces cancel out and have nothing to do with the overall movement of the object. And so we have to define the boundaries of the system that we're dealing with in order to know which forces are external and which ones are internal. So that's something we're going to have to keep an eye on. So the example on page 217, you've got people pushing on the back of a car. Obviously, that's an external force to the car, but there might be a person sitting in the car. That's an internal force. The person is exerting a downward force because of their weight sitting on the seat. That's an internal force. If they stick their foot out the door and push Fred Flintstone style, then that becomes an external force, but they're not doing that at the moment. So a free body diagram would take the form of considering the car itself as a single point, and you would add in the forces of the two people, F1 and F2, pushing in one direction. And of course, you have a frictional force pointing in the opposite direction. And we don't know exactly how big that is, but we'll guess that it's probably not as great as the force of the two people pushing on the car. But in addition, of course, you have the force of weight pressing directly downward, not only the weight of the car, but the weight of the person sitting in the car, and also any Y components of force that are being added by the people pushing the car. That's assuming that they're not pushing it straight across in the X direction. And in the opposite direction from weight, you have the normal force of the car. I'm sorry. Since the car is not accelerating up or down, that would imply that there must be no net force in the Y direction. And that would imply that the opposing force to weight, which is called the normal force, must be of the same magnitude as the weight, because they essentially cancel each other out. You could also look at this as a coordinate plane diagram, where you basically center all of the forces at the origin. And we have force 1 and force 2 both pushing to the right. And then we have the force of friction pushing toward the left. And in this case, we filled in the net force, which is the difference between the magnitude of the friction and the total magnitude of the force of the two people pushing on the car. The difference is F net, and it will be in the direction of whichever force is greater. So in this case, F net is to the right. And then we also have weight and the normal force canceling each other out. A tow truck comes along and hooks up the car, and it exerts more force on the car than the two people pushing did. So of course, the acceleration once the car is on the back of the tow truck will be much greater than it was when the two people were pushing it. And the acceleration of a given mass is directly proportional to the net force on the object. So acceleration is directly proportional to F net. Sorry. For a given amount of force, acceleration is inversely proportional to the mass of the object. Okay, so acceleration is proportional to 1 over m. So if you're pushing in two objects with the same amount of force, one of them is twice as heavy, the acceleration is only going to be half of what the lighter one is. And if you combine the proportionalities, you come up with the equation F net equals mass times acceleration, or the most common way it's written is in the scalar form, which is just F equals ma. And F equals ma is where you just take the magnitudes of the force and the mass and the acceleration, and you don't worry about it, direction. Using the scalar form of the equation just kind of implicitly assumes that the force and the acceleration are in the same direction, because otherwise you really should be using this. Because if force and acceleration are not in the same direction, then you're going to get the wrong answer from the scalar form of the equation. Okay, so an example that I'm calling Lawnmower Man is a guy pushing on a lawnmower. And you know that a person pushing on a lawnmower, get ready to be dazzled by my artistic skills here. So there's your lawnmower, and here's a guy pushing on the lawnmower. Of course, the force that the guy is exerting is going downward at an angle. It's not going straight across. And so we're going to have to maybe keep that in mind when we work on this problem. And the problem is, if the net external force on the lawnmower, that is the force of the guy pushing it minus the friction, is 51 newtons, which would be equivalent to 11 pounds, parallel to the ground. So actually what that means is that the X component of the force is what we're talking about here. That's what the 51 newtons is, the X component of the force parallel to the ground. So we don't have to go through the equations to find out what the X component of the force actually is. The actual force, of course, being diagonal. So we're assuming that the X component is 51 newtons. And the mass of the mower is 24 kilograms. What is the acceleration? Well, if you take the equation F equals ma, that is F net equals ma, then the acceleration will be F over m, force over mass. 51 newtons divided by 24 kilograms gives us 2.125, and the units do come out to meters per second squared, because 1 newton is 1 kilogram meter per second squared. So if you divide this unit by kilograms, the kilograms go away and you get meters per second squared. Okay. And the direction is the same as the direction of the net force, and that's normally the case. We have another question. Oh, and this is a way of drawing a free body diagram of that situation, with the dot being the lawnmower. You have the force pushing horizontally being 51 newtons, and that is the net force. It said so right in the problem. And you have friction pushing the other direction, but again, the force pushing forward is 51 newtons greater than the friction. So that's why it's called the net force. And then, of course, the lawnmower has a certain weight, and that is counteracted by the normal force pushing in the opposite direction. Another question involves the RMS Titanic. If the mass of the Titanic were 6.0 times 10 to the 7th kilograms, and I believe that's about what it was. And the net force of its engines is 6 meganewtons. No, so that's capital N, so that's meganewtons, or 6 times 10 to the 6th newtons. What is the acceleration? Okay, that's simple enough. Acceleration is force over mass. Force net, that is, over mass. And the net force, it is said here, is 6 times 10 to the 6th newtons. And the mass is 6 times 10 to the 7th kilograms. That comes out to 0.10 meter per second squared. So even though its engines are putting out a huge amount of energy, it's not moving very fast. And we have here a couple of questions about comparing forces. So in part A here, you have an example of a car traveling at constant speed at 10 meters per second. And which is bigger, the force of the engine, which is pushing forward, or the force of friction, which is pushing backwards? You would probably be very tempted to say, well, the forward force must be greater because the car is moving forward. And that seems like a perfectly reasonable and logical answer. But remember, F equals mass times acceleration. If acceleration is 0, in other words, if the speed is constant, then the net force must be 0. So if the car is moving at a constant speed, there's no acceleration. And that means no acceleration means no net force. Now there can be forces on the car, but they all cancel each other out. And so what that means is that the forward force of the engine is canceled out by the backward force of the friction. So the vector F engine is equal to negative the vector of F for friction, and the magnitudes are equal. So if you take the absolute values of those two terms, they'd be equal to each other. So no acceleration means no net force, even if the object is moving. It's unbalanced forces that cause acceleration. If the same car is accelerating in the forward direction at 10 meters per second squared, which force is greater? Well, in this case, we've got acceleration that's not 0, so the forces must be unbalanced. And that means that the force in the direction of acceleration must be greater. So F net in the direction of acceleration, that means that the magnitude of the force from the engine must be greater than the magnitude of friction. Okay. In part A, the magnitude of the force of the engine would have to be greater than the magnitude of friction at first, just to get the car moving from rest. But once it's up to a constant speed, the two forces will be equal to each other from that point on until it starts accelerating or decelerating. And then you'll have a net force again. Okay. There's now also a question about the thrust of a rocket sled. Thrust is just another name for force. It's used generally with things like jet engines and rockets, I guess because it sounds more impressive than force, but that's essentially what it means. And a rocket sled is kind of like a very robustly built snow sled, like you might have used when you were a kid, only it's mounted on rails to control its direction. And it has some rockets mounted on the back of it to push it forward. The magnitude, what we want here is the magnitude of the force of each rocket on this sled, or in other words, the thrust on each rocket. If a 4-rocket propulsion system, that is, there are 4 rockets mounted to this sled, can accelerate a 2,100 kilogram. Now, 2,100 kilograms is probably about 4,500 pounds, or over 2 tons. So this is a pretty robustly built sled. And if those rocket engines can accelerate the sled at 49 meters per second squared, and the force of friction is 650 newtons. So in the free body diagram, what we've got here is a point representing the sled. And of course, the sled has a certain weight. which is canceled out by the normal force because the sled is not accelerating up or down. And then you have the thrust of the 4 rockets. And I intended to draw all of these arrows the same length because we're assuming the rockets all have the same thrust. And then you have the backwards force of friction. Since the rocket sled normally moves forward, we're assuming that the total thrust is greater than the magnitude of the friction. And so Newton's second law tells us that the net force is equal to mass times acceleration. Well, we know the mass and the acceleration of this rocket sled. The mass is 2,100 kilograms, and that is the unit you need for this equation. And the acceleration is 49 meters per second squared, and those are the units you need for the equation also. So that gives us a net force of 102,900 newtons. And that's a lot of force. Now, note that that's the net force. It's not the total force of the 4 rockets, because some of the force of the 4 rockets, this is the force that goes into accelerating the sled. Some of the force from the 4 rockets goes into counteracting friction. So F net basically includes enough force to overcome friction. And so in other words, the total force of the rockets would be 102,900 plus 650 for the friction. And that means that the total force of the rockets collectively is 103,550 newtons. And so you had to add in the friction because what we found was the net force, not the total force. The force of each rocket will be that divided by 4, which is 25,887.5, or to a reasonable number of significant figures, 2.6 times 10 to the 4th newtons. This problem can be approached a different way, and you can end up with the same result. You can just say, okay, F net equals mass times acceleration, and F net is 4 times thrust of, 4 times the thrust of one of the rockets minus friction. So what we have here is mass times acceleration equals 4t minus F. And so you can just rearrange that. 4t equals ma plus F. And if you want t, it's just ma plus F over 4. So mass 2,100 times acceleration 49 meters per second squared plus F friction, which is 650 newtons, divided by 4 is 2.6 times 10 to the 4th. So you can do it either way. They're both equally valid, and whichever way makes more sense, you can adopt that as your way for doing problems like this. The next example involves a 550 kilogram sports car colliding with a 2,200 kilogram truck. The net force on each vehicle is only the force exerted by the other vehicle. And if the magnitude of the truck's acceleration is 10 meters per second squared, what is the acceleration of the sports car? So the magnitude of the force from the truck is equal to the magnitude of the force from the car. And that means that mass times the acceleration of the truck, that is the mass of the truck times the acceleration of the truck, should be equal to the mass of the car times the acceleration of the car. The mass of the truck is 2,200 kilograms. And the acceleration of the truck is 10 meters per second. And that should equal the mass of the car, which is 550 kilograms times the acceleration of the car. And if you want acceleration of the car, you just divide both sides by 550 kilograms. Notice kilograms cancel as a unit, and you end up with meters per second squared. And the number is 40 meters per second squared. So the car has an acceleration of 40 meters per second squared. Since forces and acceleration are vector quantities, we will often have to deal with the X, Y, and Z components of forces. And so you can look at basically the X, Y, and Z direction separately when there's more than one direction involved. and solve them separately and then put them back together for the overall result. Okay, so the in the x direction, the net force in the x direction, or this is the Greek letter sigma, which means summation or total of all of the forces in the x direction, is equal to the mass times the acceleration in the x direction. And the same is true for the y direction, and the same is true for the z direction. You're just using, for force in the z direction, you're using the acceleration in the z direction. Okay. And so an example on that where you use 2 dimensions at least is the force on a soccer ball. We're talking about a ball that's being kicked straight across a field, so it's not rising or falling as it moves, but it is moving in both the x and the y directions diagonally across the field. And this 0.4 kilogram ball is kicked across the field by a player. Its acceleration, because there's more than one direction involved here, the acceleration is given in terms of unit vectors. So it's 3I plus 7j meters per second squared. And the question is, what is the resultant force on the ball? And question B is the magnitude and direction of the resultant force. Now, F net equals mass times acceleration. And in this case, the acceleration is given in the form of a vector equation using unit vectors. But it's actually quite easy because if you remember that mass is a scalar quantity, you can just multiply the coefficients of the unit vectors by any scalar you want. So what we have here is mass times acceleration is 0.4 kilograms times 3I plus 7j meters per second squared. And that becomes 1.20I plus 2.80j, and kilogram meter per second squared is a Newton. So that is the net force in terms of unit vectors. For the mass and the direction, we treat that very much the same as we've been doing. So the magnitude of the force, or the magnitude of the force in whatever direction the ball happens to be traveling, is just the square root of the x term squared plus the y term squared for the force. So that's square root of 1.20 squared plus 2.80 squared. And that comes out to 3.05 newtons for the force of the ball in the direction it's moving. The direction itself is the inverse tangent of the the y component over the x component. So that's inverse tangent of 2.80 over 1.20, and that works out to 66.8 degrees. Okay, so basically, one player was here, and he kicks the ball, and it goes at a direction of 66.8 degrees, which would be probably something like that, with a force of 3.05 newtons. Okay. In the next example, we want to find the mass of a car if a net force of negative 600j newtons produces an acceleration of negative 0.2j meters per second squared. So this car is moving in the y direction only. And so this might be, it might seem simpler than it is. Force, of course, the net force is mass times acceleration. And the mass then would be force divided by acceleration. But the problem here is that force and acceleration are both vector quantities, and you cannot divide one vector quantity by another. It doesn't work. So, oops. Well, fortunately, this car is only moving in one direction, and that means that we can use the scalar form of the equation. So the answer wanted, which is mass, is also a scalar quantity. So you don't really need to know about direction. As long as the force and the acceleration are in the same direction, you're okay. So mass is just force over acceleration. It's going to be 600. And again, if you're just taking the magnitude of the force, you're not using it as a vector. You just use the absolute value of the number. So that's 600 newtons divided by 0.2 meters per second squared. And that's 3,000 kilograms. That's one really heavy car. That's like maybe a full-size, fully optioned Chevy Suburban type vehicle there. Probably even bigger than that. Maybe a Hummer. Okay. So from there, we can move on to another example along similar lines. Here we have multiple forces acting on a single particle. The particle has a mass of 4 kilograms, and it's being acted on by 4 forces, which I've sketched out to the best of my abilities here. And what is the acceleration? The magnitudes of the forces are given here as F1, F2, F3, and F4. Force 1 is 10 newtons at 30 degrees. So here's F1. Force 2 is 40 newtons at 270 degrees. 270 degrees happens to be straight down along the y-axis. Force 3 is 5 newtons at 180 degrees. And so there's force 3. Of course, 180 degrees happens to be straight to the left along the x-axis. And force 4 is 2 newtons at 90 degrees, which happens to be straight up along the x-axis. And these last three, the angles really help because it makes the problem much simpler. So first we have to resolve F1 into X and Y components. And for the others, it's really obvious what the X and Y components are. So I'll just explain it as we go along. But for F1 in the X direction, it's the magnitude of F1 times the cosine of the angle. So it's 10 times cosine 30, that's 8.66 newtons. Force 1, the Y component is the magnitude of the force times the sine of the angle. So that's 10 times sine of 30, or 5 newtons. For force 2, that's the one that points straight down. Well, obviously, the X component, if this force is running right along the Y-axis, its X component is 0. Because it's not moving to the side at all. It's going straight down. And its Y component will be the whole thing. So its Y component will be 40 newtons. For force 3, that's the one that's pointing straight to the left. Obviously, it's all nothing but X component because it's pointing right along the X-axis. So the X component is 5 newtons. That is, the magnitude of it is 5 newtons. And the Y component is nothing because it's not moving up or down at all. It's just moving straight to the left. And then for force 4, similarly, it's along the Y-axis. It's going straight up and down. So its magnitude is entirely Y component. So the Y component is 2 newtons. And the X component is 0 because, again, it's not moving horizontally either way. So if we want the sum of all the forces in the X direction, that's going to be the mass times the acceleration component in the X direction. Well, only F1 and F3 have X components. Notice for F2 and F4, the X component is 0. So, and F1 and F3 are pointing in opposite directions, more or less. So we would subtract them. F1x is 8.66 minus 5 newtons, which is the X component of F3. And that equals the mass times the acceleration in the X direction. And that is has a resultant of 3.66 newtons force in the X direction. And that is mass times acceleration in the X direction. And so if you take the force divided by the mass, 4 kilograms, you find the acceleration in the X direction, which is 0.915 meters per second squared. For the Y direction, you do the same, well, same idea anyway, not exactly the same thing. In the Y direction, let's see, in the Y direction, 1, 2, and 4 all have Y components, but force 3 does not have a Y component. And so we need the Y components for force 1 and 2 and 4. And that will give us mass times acceleration in the Y direction. So the Y component of force 1 is 5. And the Y component of force 4 is 2. So we add those together. But force 2 is 40 in the opposite direction. So we subtract 40 for that. and that is mass times acceleration in the y direction. And we come up with negative 33 newtons is mass times acceleration in the y direction. When you divide that by 4, you get the acceleration in the y direction, which is negative 8.25 meters per second squared. Okay. The vector equation for the acceleration would be just multiplying the magnitudes of the acceleration in the x and y directions by the corresponding unit vector. So the vector equation for the acceleration would be 0.915 I minus 8.25 J meters per second squared. And the magnitude would be just the x component squared, or the square root of the x component squared plus the y component squared, which comes out to be 8.30 meters per second squared. That's the magnitude of the acceleration. And the angle would be the inverse tangent of the y term over the x term. Remember, the y term is negative, so it's negative 8.25 over 0.915. Okay, and so that's the tangent of negative 9.016, and that's negative 83.7 degrees, or if you want to go around counterclockwise, that would be 276.3 degrees. Okay. So negative 83.6 degrees. I'm looking for a pencil to do it in because I don't want it to be permanent. Would be basically this direction here, something like that. You can also look in this example at the net force on a car. The mass of the car is 1,000 kilograms, and it's on ice, so we're assuming there's no friction. Of course, even on ice, there's some friction, but it's small enough that we don't have to worry about it for this problem. And so I've drawn a diagram here where the car is pretty much facing in the y direction, and the positive y direction is going up in this diagram. And we have basically a force of 450 newtons that's acting at 30 degrees from straight ahead, to 30 degrees to the right of straight ahead. And we've got a force of 380 newtons that's acting at an angle of 10 degrees to the left of straight ahead. And we want to know what the net force on the car is. So the first thing you do is break down those forces into their x and y components. The y component of force 1 is going to be the magnitude of the force, so 380 newtons, times the cosine of the angle, which we're taking as 10. We're using straight ahead as the reference for the angles. So that's 10, and that's 374.2 newtons. And the x component of force 1 would be 380 times the sine of 10, which is negative 66 newtons. That makes sense because the x component of force 1 is pulling to the left. So it should be negative. For force 2, the y component is the magnitude of the force, which is 450 newtons, times the cosine of the angle, which is 30 degrees from straight ahead. And that's 389.7 newtons. The x component of force 2 is going to be 450 newtons times the sine of 30. And that is 225 newtons. The net force in the x direction will just be the sum of the, since there's no friction here, for the net forces, all you have to do is add up the components in that direction for the different forces that we have. So the net component for the x component of the force will be F1x plus F2x. F1x happens to be negative, so that's negative 66 plus 225. And that comes out to 159 newtons, positive, meaning to the right. And the net force in the y direction is going to be F1y. I don't know why that came out looking so much like a 2. F1y plus F2y, and that's 374.2 plus 389.7. for a total of plus 763.9 newtons, and it's positive, so that would mean up or forward in this diagram. And so now that we have the net forces, we can find the net acceleration. The vector equation for the net force would be 159I plus 763.9 J newtons. The acceleration would be the force divided by the mass. And you can divide vectors by scalars. Mass is a scalar, remember. So essentially, we're just taking this equation here and dividing it by 1,000, or multiplying it by 1 over 1,000, if you want to think of it that way. And the result for the vector equation for the acceleration is 0.159I plus 0.7639 J meters per second squared. All right. Newton's second law can also be related to momentum. The actual statement that Newton left for his second law is the instantaneous rate at which a body's momentum changes is equal to the net force acting on it. And so you can look at that as net force being equal to dp dt, where p is momentum. And momentum is mass times velocity. So he was actually saying that net force changes the object's momentum. And we usually interpret that as changing the acceleration, which it does. That's also true. But he really said momentum. And so the momentum is just a way to relate the force on an object to its mass and velocity. Momentum in physics is usually symbolized by p, and it is a vector, and that will be equal to mass times velocity, which is also a vector. And so we can substitute F net equals dp dt with F net equals dmv dt. And we can separate out the m because the mass is not changing. So that's mass times dv dt. And dv dt is the change in velocity with respect to time, which is acceleration. So we've basically just proven that Newton's original statement and force equals mass times acceleration are actually the same thing. They actually mean the same thing. Okay, so here finally, at long last, we come to section 5.4, where we actually get a hold or a handle on how to distinguish or how to relate mass and weight to each other. We've had the definitions of mass and weight in the past, but we haven't really seen much about how they actually relate to each other numerically. So we know that mass is a measurement of the amount of matter in an object or a sample, and the SI unit for mass is kilograms. And we also know that weight is a downward force, well, toward the center of the earth anyway, caused by gravity pulling on your mass. And the SI unit for weight is newtons. And 1 Newton under Earth's gravity, being a physics class, which includes astronomy, we do have to specify that we're staying on Earth here. So under Earth's gravity, 1 Newton is equal to 0.225 pounds, or 1 pound would be equal to 4.44 newtons. So that's a relationship you can use for converting back and forth as long as you're on Earth. Okay, so weight and gravity are related to each other, of course. Weight is a force, and gravity is a form of acceleration. So it's not really surprising to see that the equation for weight in Newtonian physics is analogous to the equation for force. Force equals mass times acceleration, and weight equals mass times gravity. Weight being a type of force, and gravity being a type of acceleration. If all you need is the magnitude and you don't care about the direction, then weight is just mass times gravity. Of course, I mean, with weight, it's normally going to be downward anyway, but you know, there is a scalar form of the equation too. If the net external force on an object is its weight, then it's in free fall. That's ignoring air resistance because that's what Newton did. Because we want an idealized situation. If we throw in air resistance, the problem really is that air resistance will be different on different days in different places, depending on things like temperature and pressure and wind speed and wind direction and stuff like that. If you want to get to the sort of the kernel of what's really going on, you want to cancel out stuff like that that can vary a lot from one day to another or one place to another. So that's why we tend to ignore air resistance. So if the net external force on an object is its weight, weight is, of course, due to gravity. And so, as we said in the last chapter, if something is moving under the influence of nothing other than gravity, then it's in free fall. Well, if the net external force on an object is its weight, then it is moving under the influence of nothing but gravity, and it's in free fall. Gravity on the surface of the Earth varies a little bit from place to place, and it also varies a little bit with altitude, but it's always right around 9.8 meters per second squared. And that's why we usually only use it with two significant figures, because the third significant figure often varies from one place to another. So, but it always rounds off to 9.8. Sorry. So we have a problem here. Okay, I see that we've kind of gone past our time on the remainder of this lecture. So I'm going to cut it off there and start up here next time. So we'll do the example of clearing a field at the beginning of our class next Monday. Okay, so I'll see you then. Happy Thanksgiving.